Hi, and welcome back to my Physics Online video lecture series. Today's video, we're going to be looking at Newton's third law. In some sense, this completes the cycle of Newton's laws, although there will be some additional lectures for you to watch about forces. Now, in the past, I've already made some videos that kind of summarize Newton's laws. I've made one about Newton's first law, I've made one about Newton's second law. This finishes that sort of series of videos. Newton's third law, you'll recall, is the only one that was, as best we know, originally formulated by Newton. However, in putting this with the other laws, you get a kind of synthesis that wasn't really there prior to having them. And that synthesis becomes sort of like the, in some sense, classical method for dynamics, for classical dynamics. And so it is truly a very important contribution to physics, one of many contributions to physics and mathematics made by Sir Isaac Newton. So what does Newton's third law say, and what is it? Well, Newton's third law is sometimes called the action-reaction law. So I'll just put that parenthetically at the top, action-reaction law. Essentially, it's a law that governs interactions between two objects. So you need two objects for the Newton's third law to be invoked. So let's say that I have object number one right here. Maybe it is a box. I have object number two, maybe a person, and they are trying to push on the box. So the person is pushing on this box with some force. We'll call this F on object one by object two. Well, that would result in the box pushing back on the person with a force. We'll call this F from object 2 on object 1. And Newton's third law basically says that these two forces, F12 and F21, are equal in magnitude but opposite to each other in direction. So first of all, note that I'm pronouncing these as F21 and F12, or negative F12. It's not F21, it's not F12. It's force of object 2 on object 1, it's force of object 1 on object 2. And in equation form, that's really all there is to Newton's third law. You have a pair of forces and they are equal to each other and they are in opposite directions. So this is your action-reaction law. This person pushing on the box might be the action. The reaction might be that the box pushes back on the person. So put differently, we might say that each applied force produces a second force, a reaction force in other words, of equal magnitude but opposite direction to the original force, or the original action force. We could say, maybe call it the original action force. Important note about this, these two forces act on different objects. So these two forces do not act on the same object. Now let's consider some conceptual questions to go with this. And maybe before I get into the conceptual questions, it's worth noting that simple as this equation is, it's quite profound and it's quite a useful tool to have, especially for those of you who are taking a physics course because you are pre-med and you're going to be doing MCAT or pre-optometry, you're going to take the OAT, something like that. They are very profound in that this equation will pop up throughout physics 1 and 2, but it will do so subtly. And just kind of look for it as you take those courses. Go looking and seeing, when do I have a Newton's third law pair of forces? Because very often it either serves as a double check, or if you're ever taking like an MCAT, it might serve as a shortcut to getting to the answer to a question that's being asked. All right, let's do a conceptual question here. And the conceptual question that I'm going to ask is, do we have a Newton's third law pair in each of these cases? So case number one, let's say that I have an object and it's sitting on top of the table, and you have the force of gravity acting downwards on the object, and you have that the table is pushing upward on the object, applying what's called the normal force. So are the normal force and gravity a Newton's third law pair? For each of these, you might pause the video and try to answer it or puzzle it out, and then play to get the answer. So we have gravity and we have the normal force. Is this a Newton's third law pair? The answer is no. It's not actually a third law pair. Why is it not a third law pair? Well, both of these forces are acting on the box. So they're acting on the same object. And they're kind of existing for different or from different things applying it. The normal force is due to the table that the box is sitting on, whereas gravity is from the earth. So the follow-up question might be, what is the Newton's third law pair for each of these two forces? Because there must be one for each. Again, you might want to pause the video, try to answer that, and then start it back up to get the answer. So go ahead and pause. All right, if you've taken some time to think about it, here's what the basic answer is. For this normal force, the Newton's third law pair would be that the box applies a normal force back on the table. For this gravitational force, essentially the Earth is pulling on the box, so the Earth pulls on the box with gravity. We could say maybe via gravity. And the Newton's third law pair is the box pulls back on the Earth. So that is a Newton's third law pair. But the normal force and the gravity themselves, that is not a Newton's third law pair. A follow-up question. Again, I have my box, and I've got gravity pulling downward on the box. Maybe it's been tossed up in the air. And then somewhere down here is the Earth. And the Earth is being pulled up with gravity towards the box. So we could say that this is force on box from Earth. This is force on Earth from box. And so the question is, which one is larger? Is the Earth pulling with more gravity on the box, or is the box pulling on the Earth with more gravity? Again, you might pause if you're watching this, make a guess, and then come back. The answer is they are equal. So they are equal in magnitude. This is due to Newton's third law, which says that the amount of force that the box applies to the Earth and the amount of force that the Earth applies to the box must be equal to each other. That means that the box is applying the same amount of gravity on the Earth as the Earth is applying on the box. Third conceptual question that goes with this set of Newton's third laws. So we have a pair of ice skaters. They're on this nice icy surface with almost no friction at all. The two of them push off of each other. This one pushes, this girl pushes off the boy with 10 newtons. The boy pushes back, also 10 newtons. Do the skaters move as a result? Again, pause the video, try to answer it, and then see what the answer is. The answer is yes, they should accelerate. So they will accelerate. Do they both have the same acceleration? No, because they may have different masses. But the two forces in question are acting on different people. So you have 10 newtons on this person right here, and so this person's system taken in isolation looks like this. You have 10 newtons on this one right here, so this guy's system taken in isolation looks like this. Each one, we could call this 1 and this one 2. For the first one, we would have 10 newtons is mass of number 1 times acceleration of 1. For 2, we would have 10 newtons is mass of 2 times acceleration of 2. They both have 10 newtons. The 10 newtons are in opposite directions. They may have different accelerations on account of different masses. For example, if this one is 60 kilograms and this one is 50 kilograms, then our accelerations will be 1/6 of a meter per second and 1/5 of a meter per second, respectively. So A1 would be 10 newtons over 60 kilograms, which is 1/6 meter per second squared. A2 would be 10 newtons over 50 kilograms, which is 1/5 of a meter per second squared. Okay. That's all that I'm going to do in today's short video on Newton's third law as far as conceptual questions go. Maybe the last little point is, in what sense does this tie all of Newton's laws together, or in what sense do we get dynamics out of all this? And the answer is, with Newton's first law, we have a law that says if the net force on an object or a system is 0, then the object or system will have a net acceleration of 0. In other words, it will retain whatever quantity of motion it has. Newton's second law says that if there is a net non-zero force on an object or system, then that object or system will accelerate according to F equals ma. Newton's third law basically says if you have two objects that interact, in other words, if some object applies a force to some other object, they form a system, and within that system you have a Newton's third law pair, which within the system cancels. For each object it doesn't, but for the system it does. And that implies that there must be some quantity which remains conserved for the system as a whole. That quantity must be related in some way to the velocity of the objects within the system. And that quantity we will introduce in a future series of these lectures. That's all for today. Hope you learned something, and thanks for watching.